Hello everyone, this is Mustafa here, solving soil mechanics problems for civil engineering students. In this video, I am talking consolidation, and today I'm covering question number 5. Let us see what we've got here. So this is a set of data from consolidation test. We are given the vertical stress sigma dash or sigma dash z versus the height of the sample, and we are required to plot the E log sigma dash curve and determine the compression index C sub C. Solution strategy for problems of that nature. First, we need to process the height to get the void ratio because we are giving here the height rather than the void ratio E. Second is to be able to plot the E log sigma dash graph and use the results to get the compression index C sub C. Essential knowledge. We need to know the phase relationships, and we need to know how to determine the void ratio from basic data, and we need to understand the definition and the determination of the compression index. Let us see how we can solve this problem. Here we have the phase diagram, which I covered in some of my previous videos. So what we've got here is when we have a sample and the VV is the volume of voids, when the sample compresses by delta H, so we will have a corresponding reduction in the void ratio delta E, and the relationship is a change in height divided by the height equals the change in the void ratio divided by 1 plus the void ratio. Let us first calculate the initial void ratio E naught. The formula that we need to know, you can memorize it, but normally it is given in exam or it is in a textbook. We have here 1, 2, 3, 4 quantities. Actually, if we ignore the water as being of known unit weight, so we have here 3 quantities. That's the dry unit weight equals the specific gravity times gamma water divided by 1 plus the initial void ratio E naught. From this, actually, if you know 2 values, you can get the third. The basic definition of the dry unit weight is the dry weight of the soil divided by V naught, which is the total volume here denoted as V in this phase diagram. So V naught equals the initial height times the area. So I'm giving the initial height here as 19 millimeters, so that's 1.9 centimeter, multiplied by the cross-sectional area of the sample, which is given here as 31.68. So I now calculated the initial volume of the sample in centimeter cubed. So the dry density then, you see, when we use gamma dry, it is the unit weight. When we say gamma, it is the unit weight. You will see next that its units is kilonewton per meter cubed. And when we refer to the density, which is the mass divided by the volume, we call it the dry density or the density in general. And the notion here is rho d. So the dry density from what we've got here is the mass 95.2 gram divided by the volume we just calculated. So I have here the dry density as 1.58 gram per cubic centimeter. Remember, this formula here is for the unit weight, not the density. So I can convert the dry density to dry unit weight by multiplying by G. You need to be very comfortable with this unit conversion. You multiply this by the unit weight, by the gravity acceleration, which is 9.8, that's meter per second square. So the results would be 15.5, that's kilonewton per meter cubed. So now I'm in a position to substitute in this equation here to get the required initial void ratio. So I calculated E naught here, 0.694. Why do I need to calculate E naught? Because I should use this initial void ratio to work out the rest of the void ratio based on the given height here, and using this correlation between the change in height and the corresponding change in the void ratio. So let us now try at this first pressure value of 25 kPa. What we've got is, when we have the stress equals 0, before applying any stress, the initial height is 90 millimeter, that's given to us, and the corresponding initial void ratio from this calculation here is 0.694. Now, when we have the stress equals 25 kPa, we are given height of 17.65 millimeter. That's 17.65 millimeter. We are after the corresponding void ratio E equals how much at this particular condition. We use this equation like I said here, delta H over H equals delta E, which is a change in the void ratio divided by 1 plus E, and I should be able from this to rearrange things and get delta E. So from this I have 19 millimeter, this is the initial height, minus 17.65, and this is the final height at this particular pressure, divided by the initial height, H naught, 90 millimeter, and I multiply this by 1 plus E naught, 1 plus E naught, E naught. And this has given me 0.1204, meaning that at pressure 0, or when I increase the pressure from 0 to 25, this produced reduction in the void ratio of 0.1204. And as such, the void ratio at this height is E naught minus delta E. That's 0.694, I calculated it, minus 0.1204, that's 0.574. It's important to understand what we're doing here. So because we are applying pressure, the void ratio reduces or drops by the compression. As such, you would expect the void ratio at 25 kPa to be less than the void ratio in the beginning, which is 0.694, and this is why we subtracted this change in the void ratio to give 0.574 as the sample becomes denser, if you like. Let us try another value. So when we have here the 50 kPa, we repeat the same thing again. The initial height was 19. The initial void ratio is 0.694. I can basically apply the same correlation at 50 kPa. At 50 kPa, the corresponding height after compression is 17.4 millimeter. And what would be the void ratio here? It's E naught, E naught. What is the void ratio here, E, that corresponds to that value? Exactly, we repeat the same thing again using this correlation, and I calculate the change in the void ratio. That's 19 is the initial height, and 17.4 is the corresponding height, and this has given me change in the void ratio 0.1426. So I can work out that E is equal to E naught minus delta E. E naught has not changed, it's 0.694. Delta E, I just calculated it, it's 0.1426. So the void ratio here is 0.551, and so on for the rest of these values. I can now tabulate the results. 25, height is 17.65, this value. Delta E is 0.1204, the value that we calculated from the previous page, and E is 0.574. 50, exactly the same. So I have 17.4, 17.4. Delta E, we just calculated it here, 0.14267, and the E equals 0.551, and so on. Now I'm in a position actually to draw these values. So I can draw E versus sigma dash Z. So I have these values here to a logarithmic scale, and I am in a position basically to determine the compression index. What is the compression index? Here there is a version part of the curve which indicate the range when the sample was never subjected to pressure more than this in the lab, obviously. And the gradient of this is the compression index C sub C. So what I need now is to determine this gradient C sub C. So I can come up with this triangle. So C sub C based on this is the change in the void ratio, delta E, divided by the change in the horizontal axis, which is delta log sigma. I can take this outside, and it's very important to know how to get this delta log. I said before, it's prudent when you work out this triangle, you choose the height here so that you know the values of the void ratio. So here that this tip correspond to zero point 0.5, this tip correspond to 0.4, so 0.5, 0.4, so I know delta E. Now, one log here correspond to 3.4 centimeters. You measure this by scale. So all I need to do now is to measure this also by the same ruler, and this is 2.6 centimeters. So delta log sigma based on that is just simple proportion 2.6 divided by 3.4. This 3.4 is basically the measurement that corresponded to one log unit. So you measured it between the 10 and 100, or between the 100 and 1000, or between the 1 and the 10, it's exactly the same. So based on this, the delta log is 0.765. I am now in a position to just substitute here. The compression index is this height divided by the base. So the height is delta E, that's 0.1. The base, we just calculated it as 0.65. So the compression index here is 0.13. It is as simple as that. So the lesson we learned from here is how to determine the void ratio from the basic relationships of the dry unit weight, or could be the saturated unit weight, or whatever basic information given. And then I use the correlation between change in height and the corresponding change in the void ratio, so that I can calculate the void ratio at any pressure increment. And then I can work out the compression index from the gradient of the curve. Thank you very much for watching this, and expect some more videos from me on consolidation.